All right, so I'm gonna turn down the fan. We are gonna get back into quantum field theory here. I know it's been a while, and I know that's been probably a little bit frustrating for you guys, or maybe not. I don't know, but I've always wanted to get back into this. So without further ado, let's get right into this. But before I mention this, mention getting back into this, I do plan. So there's going to be a shift in plan here. I've pre-written everything down, and I'm gonna go through it step by step, right? And by going through it step by step, I think this will be a much more enriching experience for you guys to learn the intricacies behind quantum field theory, so that you can really follow along and really understand what's going on here. Right. So let's get right into this. I'm gonna zoom in. So we're going over probability density and normalization. I figured these two things would be a good first topic to go over. So what do I have going on here? I have two Klein-Gordon equations. Okay. Why two Klein-Gordon equations? I'm really just interchanging these guys right here. They're both theoretically solutions to the Klein-Gordon equations, but I want to find out what the difference between these two equations is. Okay. And so to start off this enterprise, let's begin by considering this right here. This is the time derivative. This is the double derivative actually of psi, and then we multiply it by psi star, right? So that would be this right here, double derivative of psi times psi star. Right, so we could think about foiling this over here, and we get this. And we could think about doing the same here, right here, and foiling this over and getting this. But that's not totally true here, because if we were to perform this function right here, or this operation, we get this times this, or this times this, actually, this whole thing. But what's that? We have to take the derivative of this, right, times this, times the derivative of this, or plus the derivative of this times this. That's chain rule. I think that's what it's been a while since I've taken calculus, but that's this right here. Right, so this to here is going to be this guy, and then that guy is on the side, and this guy applied here, that's this guy. And then we're left with this guy on the side, that's this. And we're doing the same thing for this operation to these guys. Okay, and you could see how so you could see what's going to happen here. This guy here and this guy here theoretically shouldn't be different, right? The time derivative of something, it should be equivalent to the time derivative of its complex conjugate. So these guys will go to 0. Okay, and so we're left with this. All right, so let's put this on the back burner, and let's take a look at the spatial derivative now. The spatial derivative are these guys right here, and we're kind of doing the exact same thing, right? We do this times this, which is right here, and then this times this, which is right here, and then we multiply right here actually, and then we multiply this, and here he is, and so on. So you can kind of follow along now on how we get this from this. All right, and we're doing the exact same thing here as we are doing here, because we find out that the spatial derivative of the spatial derivative of the complex conjugate is no different than the spatial derivative of the original function, right? So therefore this goes to 0. All right, so what do we have now? Let's go back to our Klein-Gordon equations. We're trying to find the difference between doing the Klein-Gordon equation on your function and then multiplying it by a complex conjugate, and doing it on the complex conjugate and multiplying it by the function itself. So this minus this, right? So that's this right here and this right here. Remember, we have to multiply this guy over too. This is what we're doing to the whole equation. Okay. So, and then we're doing the same thing to this guy right here. And you notice I'm not really putting mu's in here, because what actually ends up happening is that this minus right here will make that a plus. And since this is a minus right here, the mu's are going to cancel out. So I'm not even bothering with the mu's. So we left with this, and now we have, let's go down to here now. So this right here, right, we said was this, from up here. This is equal to this, right? So this guy is equal to this guy, like right there. And then this guy is right here, right? So if this guy is right here, that means he's equal to this, right? So let's put that guy right there. Now, this is interesting. We have the time derivative is equal to a spatial derivative. The way I like to think about this is densities and currents. The reason I like to think about this is the reason I think about this is, or the way I think about this is, I think about a sphere, right? Or yeah, if I think about a sphere, and then flux coming out of the sphere, right? What this is telling us is that the time derivative, or the change of anything in the sphere, is going to be due to those things leaving the sphere, right? So there's going to be a spatial, I don't know why I have two arrows coming out of this guy, but there's going to be a spatial, spatial derivative, because things will be moving out of the sphere. Things will move with respect to space. And as they move out of the sphere, the rate of change, the rate of change with respect to time inside the sphere is going to change, right? So this here is a density. The rate of change with respect to time of the density should be equal to the rate of change of space with respect to current, things flowing out of that sphere. Okay. So this here we can call a density then, and this here we can call a current. Okay. And this is something that you find a lot, especially in advanced classical mechanics too. And there's a tensor version of this too, but we're not going to go over that. Save that stuff for later. All right. Here I just have some conventional notation. So here I basically written this down, the same statement here. Time derivative of the density is equal to the spatial derivative of the current. All right. So now we have, okay, so that's that. Let's consider now this right here. I want to consider a solution. And by considering the solution to be this, we're going to come across some interesting notions, right? So we're going to consider the solution to be this, or to take this form. It looks a little bit arbitrary right now, but we'll see why. We'll see why it takes this form. So that means, so by de facto, the complex conjugate is, there's no minus right there, right? So anything with an I in it, we have to change to a plus I. And everything else, and this guy also, or if we're going to assume that this guy's complex as well. So we complex conjugate this guy when we complex conjugate this, and we complex conjugate this when we complex conjugate, right? A lot of complex conjugating. And that we'll see that quite frequently in quantum field theory. A lot of complex conjugating. fix a little something there. Let's see. So, yeah, so we're at this point where we have defined a complex conjugate to our proposed solution. Okay, and so what we want to do now is we want to take the time derivative of this, because we're taking the time derivative of this, and here that is. The reason we have this out here, this guy right here, is because we can sort of think of this as, we could sort of think of this guy right here as a wave that looks, if we were to expand out its exponents, it would look something like this. I, k, 0, x, 0, and x 0 is just t. That's usually the time component. All right, and then we have all the spatial components. So I, k, negative I, k, 1 times x, 1 plus negative I, k, 2, x, 2, and so on. These are the spatial components. Spatial components, and this is the temporal component. And when we take the time derivative of this guy, when we take the time derivative of this, ultimately these guys are going, we're kind of doing a chain rule, right? We want the derivative of the inside, which is really just going to be this, because we're taking with respect to time. So it's going to be this right here, and k naught is omega, right? It's the angular momentum, so it's going to be omega k, right? So that's where that is right here, okay? And we also have this negative I right here as well. And I'll put that negative I in. I think I forgot to put the negative I in. Okay. But negative I is not going to matter anyways, because we're going to have complex conjugates canceling each other out, I think. But should I put it in? Yeah, I'll put it in. Let's see here. So there's going to be an I right there, and then an I at this time derivative as well. So we can make sense of going for, we're doing this right here, right? We're just really kind of interested in this now. We're not really looking at this anymore. This was just an interesting relationship. We were able to recover a basic rule of advanced classical mechanics if we were to define our density and our current in these ways, in terms of our wave functions. Right, so if we were to define them like this, then we can be ensured that this will hold, because we've derived it from here again. But let's get back to the pressing issue at hand, which is taking a look at this density right here. So we've come to this point. What now? Well, from here, we have, let's see here. So this is right here, right? And then this is right here. These two guys are the same. And what am I doing? So I want to find the integral of the density over space. And this is going to give me some volume, right? So I'm taking this integral right here and with respect to space. And so what do we get? Well, we're going to be able to factor out these omega k's, right? And we're also going to be able to factor out these i's, but again, we have a negative I and a positive I. Negative I times negative I times positive I, well, that's going to be, if I is the square root of -1, we have the square root of -1 times the square root of -1. I'm going to do this here. I'll make it very explicitly clear here. Square root of -1 times the square root of -1 is -1, right? But if we have a negative, it's just 1. So ultimately, those i's aren't going to matter. That's why I didn't really include them. So we can sort of forget about the i's, and we can go back to the issue at hand. All right. So this times this is just the inside because they're square roots. So we have this. Bring this out because that's just a constant. Right? And we're able to do this because it also shows up right here. So I'm bringing that guy out too. So this guy should have an omega k right here too. But what I'm doing is kind of shorthand, which is kind of not good, like that. And I'm canceling out those guys altogether. But again, you don't have to do that. You can bring your omega k, which was right here, and bring it out here, and then do the canceling. Right? So then we have this times this times this, and then we have an integral over 3 dimensions of space, which is a volume. Right? So we can cancel out this volume with this volume. Okay? And we're doing the same thing on this guy here, and what we get is this 1/2. Now there's these two right here. So we have 1/2 of this plus 1/2 of this. Well, these guys are, they're exchanging the order shouldn't matter. So 1/2 plus 1/2 equals a whole of that, and so we end up with just this. We had to get rid of the integrals because the integrals define this volume, and then we were able to cancel those volumes out. Okay, so this right here is if this is a complex conjugate, if they were equal to one another, we get this relationship right there. Right. So what we have done is we've explained away what you might come across this in your quantum field theory textbooks. That we've explained away why exactly we have these guys show up in so many integrals, and why we have these guys show up in so many integrals as well. Right? So we have solutions. This is what our solutions look like to the Klein-Gordon equation. And what we're going to find out later is that, I'll give you a sneak peek actually. I'm going to go over, actually maybe I won't. We'll go over this later, but we'll be able to generalize this even more. Okay. But that is probability density and those normalization constants, these guys right here, for the Klein-Gordon equation. We've went through some pretty hefty math, and this is what quantum field theory is going to be all about. Hefty math with a lot of physics, but I'm going to take this chunk by chunk and piece by piece, and we're going to be able to really understand how this all works, what quantum field theory looks like. We're going to be able to decompose it. And yes, I will make a website, but currently I'm still a little too busy to be making a website right now. But I am going to post these on a website, and more that you won't see on a website, so that you can put those up, so I can put those up for perhaps a subscription or purchase for later on. But I hope you enjoyed this video, and I'll see you in the next one. Bye.